Good morning, student. In the last class, we have discussed the magnetic field due to a current carrying wire and also the force between two parallel current carrying wire. In this class, we are going to discuss about the magnetic field of a circular current loop. Magnetic field due to a circular current loop. Okay. Suppose first let's draw the XYZ coordinate system. Suppose we have a current loop in the YZ plane. Okay, it is carrying a current I in this direction, and we are going to find the magnetic field at a point in the axis of the current loop. The axis of the current loop is always passing through the center and perpendicular to the plane. Okay, suppose if this is the current loop, and if we imagine this is the Y, this is the Z axis, then axis will be along this point, passing through the center and perpendicular to its plane. Therefore, this will be along the x-axis. Okay, therefore we are going to determine the magnetic field at any point P on the x-axis due to this current loop. Okay, so this is basically the geometry. The current loop is in the YZ plane. It is carrying a current I, and we are going to determine the magnetic field at the point P, which is on the x-axis. And as I have already told, the x-axis is passing through the center of the loop and perpendicular to the YZ plane. Okay, so basically this axis. So it is on the axis of the circular loop. Okay, so for that, the procedure is similar. Let's imagine a small element dl of this current loop. Say this is a small element dl of this current loop, and now we connect this center of the dl element to the point P on the x-axis. Okay, so this is dl vector, and this will our r cap vector. Okay, and from this to this point, the magnitude of the vector is small r, and its direction is r cap. Basically, I am writing here the direction of this position vector from O to, say if this is the point O, then OP is equal to r, and its direction is r cap vector. Okay, now one thing you have to remember, that you see this is YZ plane and this is XY plane. The position vector is in the XY plane, and we are considering the DL element in the YZ plane. Okay, so as you probably know, any line in the XY plane is perpendicular to the YZ plane. Therefore, the r cap position vector is perpendicular to DL. Okay, that thing you have to know. It's not obvious from the figure, but you have to always keep in mind that r cap position vector of the point P, where we are about to determine the magnetic field, is perpendicular to the length vector dl. Okay, this thing you have to remember always. R cap is perpendicular to dl vector. So in the previous derivation, we take the angle between r cap and dl as sine phi. Therefore, sine phi in this case, sine 90 degree, will be equal to 1. Okay, this thing is the first thing you have to notice before doing the derivation. Okay, now as done in the previous case, I am first going to concern about the magnitude of the magnetic field at the point P due to the current element due to the current in the element dl. Okay, once I got this value, I can integrate the whole circular loop, and then we can find out the magnetic field at the point P. Okay, but there is a small twist here that I will tell you while doing the derivation. Okay, so first let me write the expression for the magnitude of the magnetic field. Magnetic field dB, as I have already told you, mu naught divided 4 pi I dl sine phi divided by r square. Okay, r square is nothing but the distance from this point to this point. So this is say O and this is say M point. So MP is equal to R square. Okay, and this is a right angle triangle. You have to you have to mind it because this line is perpendicular to this line. Okay, so this is a right angle triangle. Okay, so we know that sine phi is equal to 90 degree. Therefore the value is mu naught divided by 4 pi I dl divided by r square. Okay, so say OP, the distance from O to the point P, say this distance is x. Okay, and here to here OM distance is, say this is nothing but the radius of the loop, is not it? If the radius of the loop is A, then r square will be equal to how much? I already told you OPM is a right angle triangle. Okay, so r square will be equal to A square plus x square. Okay, so we can write mu naught divided by 4 pi I dl. This will be equal to A square plus x square. Okay, so finally we found the magnitude of the magnetic field as mu naught I dl divided by A square plus x square. This is the magnitude of the magnetic field at the point P due to the current element dl. Okay, now what I have to do, I have to find out what is the direction of the magnetic field. Direction is very important here, because for a vector quantity we have to know the magnitude as well as the direction of the field. Okay, so how we calculate the direction of the field? If you remember, I mean, I have written it many times that the value of dB vector, if you see your notebook, you will find mu naught divided by 4 pi I dl cross r cap divided by r square. Okay, so what we have to do, we have to find out the direction of the cross product between dl and r cap. The direction of the cross product between dl and r cap will basically going to give us the magnitude of the direction of the magnetic field. So you see here dl vector, it's almost parallel to the z-axis. Therefore if we write the dl vector, we can write it as dl into k cap, is not it? Because k vector always represent the direction in the z-axis, right? And r cap is this unit vector in the xy plane. Okay, so what we can do, I cap is equal to, if we plot this to any line parallel to x-axis, so r cap will be basically minus j cap plus I cap, isn't it? Because I cap is a unit vector along x direction and j cap is a unit vector along y direction. So using perpendicular law of vector addition, we can always represent r cap as equal to I cap plus minus j cap, because j is now along negative y direction. Okay, so we can write r cap is equal to, what we will write, minus j cap plus I cap. Okay, so it will be minus I minus j cap. Okay, so dl cross r cap will be equal to now dl into k cap cross I cap minus j cap. Okay, dl k cross I is equal to, we know, plus j vector minus k cross j we know minus I cap. Okay, so dl into I cap plus j cap. Okay, so I cap is a unit vector along x direction and j cap is unit vector along y direction. So basically whatever the direction of the magnetic field, it is going to be in the xy plane. Okay, so the magnetic field will be in the along this direction. Okay, so this is the value dB, because this is our xy plane, so magnetic field will be along the direction of xy plane. Okay, now if we see that this angle theta, that theta is the angle which r cap made with the y-axis. If this angle is theta, then this angle will be theta. It is due to what? It is because you see that OY is perpendicular to OX, since these are two the axis of the coordinate system, and DB is perpendicular to r cap. from here, you see dB is perpendicular to the plane containing dl and r. Therefore, dB is perpendicular to the position vector r. Okay, and we know that if the angle between two lines is theta, then the angle between their perpendicular line is also theta. This is a simple geometrical fact. Okay, here OX is perpendicular to OY and dB is perpendicular to r cap. Therefore, if the angle between OY and r cap is theta, then therefore the angle between OX and dB will be also theta. Okay, so dB is along this direction. Okay, so since dB is making an angle theta, therefore we can divide it into two components. The first component will be along y-axis and the second component will be along x-axis. So this component is along y and this component is along x-axis. Okay, so whatever the magnitude of the magnetic field we have found, we have to multiply it by cos theta to get the component along x-axis, and whatever the magnitude we have found, we have to multiply it by sin theta to get the component along y-axis. Okay, but there is a twist here, because you see the this circular coil is a symmetrical body, therefore there will be another element dl here, diametrically opposite. Okay, for this element also there will be another magnetic field, and the direction of the magnetic field, as you could have imagined, the direction will be along this direction. Okay, if due to this element magnetic field is along this direction, due to this element magnetic field will be along that direction, and its angle will be also theta. Okay, so we can divide this magnetic field again into two components. The component dB sin theta will be along this direction, and the component dB cos theta will be along that direction. Okay, now you see the magnitude of the magnetic field will be same, because these two are symmetrically situated with respect to O point, this dl and that dl. Therefore, the magnitude of the magnetic field due to this element at this point will be same, but their direction, you see their y component for the upper dB field, y component is along this direction, and lower dB field, y component will be along that direction. Therefore, these two components will cancel out each other. Okay, but this x-axis component, they will be along the same direction. Okay, so that component will just add up. Okay, so finally, if you are asked to find out the magnetic field, then you have to consider only the part which is along x-axis. Okay, so it means what? It means for a current carrying loop, there will be only magnetic field along the axis. There cannot be any other field along any arbitrary direction. So we have just proved the fact. Okay, so this is a very important result. I will try to repeat it again. You see, for dl element, we found that the magnetic field is along xy plane. Okay, this is the xy plane, and it's making an angle theta with respect to x-axis. The angle theta why we have obtained, I have just explained. Okay, now I can resolve the dB into two components, along x-axis and along y-axis. Along x-axis component will be dB cos theta, along y-axis component will be dB sin theta. Okay, that's fine. Now, similarly, we can consider a diametrically opposite dl at this point, because this is a symmetrical body. If we consider dl here, you can also consider dl here, because these are diametrically symmetric things. Okay, so for this dl element, there will be again a magnetic field dB. Okay, and its magnitude will be same with this. dB will be always mu naught into I divided by 4 pi dl divided by a square plus x square, but the direction of the field will be along opposite direction. Again, we can resolve it into two components. Y direction magnetic field will be like this, x direction magnetic field will be like this. Okay, now if you find out the resultant magnetic field, you can see that this magnetic field and this magnetic field opposite to each other, therefore they cancel, and finally we can have only magnetic field along the x-axis. That means for a current carrying loop, the magnetic field is always lying along the axis of the loop. There cannot be any other magnetic field in any arbitrary direction. Okay, so if I have to write the magnitude and direction of the finite field, then it will be, if I would write, then the magnitude of the field will be mu naught divided by I, mu naught into I divided by 4 pi dl a square plus x square into cos theta. How many components? There will be two components. So I have to write 2 mu naught into pi, mu naught into I divided by 4 pi dl a square plus x square into cos theta, and its direction will be along I cap, along the x-axis. X-axis is here. Here what direction? Is a perpendicular to the plane containing the word and passing through the center. Okay, so the x-axis is nothing but the axis of the circular current loop. Okay, so this is our final value of the magnetic field due to this combine these two diametrically opposite current loop. Okay, current element. So in the next part, what I am going to do, basically I have to integrate this whole expression for the whole conducting loop. For one part dl, I have evaluated the magnetic field. Now for the whole current loop, what we have to going to do, we are going to find out the magnetic field. And how we can do, we have to just integrate along the perimeter of the loop, then we can find out the magnetic field. Okay, and also already we know the direction of the magnetic field. Then in the next part, what I am going to do, I am just going to integrate the dB to find out the magnitude of the magnetic field. Then we know the direction, so we can finally evaluate the magnetic field due to this whole current carrying loop at the point P on the x-axis, that is on the axis of the loop. Okay, thank you. So in the next part, I am going to do that. Okay, so let's continue from the last part of the lecture. We have found the magnetic field due to the current carrying element IDL at the point P, and its value was given as dB vector is equal to mu naught divided by 4 pi I if you remember from the last part, I dl divided by a square plus x square cos theta into I cap due to this element dl. Okay, now to find out the a magnetic field due to the whole current loop, we have to basically integrate across the circumference of the loop, or across the perimeter of the loop. Okay, so basically we have to integrate the value dB along this part. Okay, so that will give us the total magnetic field at the point P due to the whole current carrying element. Okay, so let's do that. So 0 to B dB mu naught into I divided by 4 pi. This is a constant quantity, so let's put it like that, dl a square plus x square into cos theta. Okay, and its direction is I cap. Okay, its direction is I cap. Okay, now from the figure you can see, consider the triangle OMP. OP is perpendicular, OM is base. Therefore, cos theta is equal to how much? Cos theta will be OM divided by MP. Okay, what is the value of OM? OM is nothing but A. And what is the value of MP? MP is nothing but, this is a right angle triangle, right? So R square will be equal to A square plus X square. Therefore, OP will be root A square plus X square. Okay, so we'll put this value here. We'll get 0 to B dB, we'll get only B vector mu naught I divided by 4 pi dl cos theta is equal to, put the value of cos theta A, and in the denominator A square plus x square multiplied by A square plus x square to the power half. So finally we'll get x square to the power 3 by 2 into 3 by 2. This whole will be in the direction of I cap. Okay, so you see now in the denominator A is what? Radius of the loop. It is a constant quantity. Okay, and for a fixed point P, X is also constant. So A divided by a square plus x square to the power 3 by 2 for this particular case is a constant quantity, so we can take it out of the integration sign. Okay, so let's take it out from the integration sign. 4 pi a square plus x square to the power 3 by 2 integration dl into I cap. Okay, so integration dl for this current loop, what it will mean? It will means the total perimeter of the circle. Okay, for example, this circle we can imagine to be consist of small dl part. Okay, all small dl will basically going to give us the circumference of the circle. Okay, so integration dl is nothing but the circumference of the circle. Circumference of the circle. Okay, and what is the radius of the circle a? Therefore its circumference will be equal to twice pi into a. So integration dl is nothing but twice pi into a. So we are going to put this value. B will be equal to mu naught I divided by 4 pi a divided by a square plus x square to the power 3 by 2 into twice pi into a. Okay, so 2 pi 4 pi will cancel out. B is equal to mu naught into I divided by 2 a will give us a square into 1 by a square plus x square to the power 3 by 2. Okay, so if we write it again nicely, then B is equal to mu naught into I divided by 2 a square divided by a square plus x square to the power 3 by 2 I cap. Okay, so this is the final value of magnetic field at any point on the axis of the loop. Okay, x axis is nothing but the axis of the loop. If the loop is, again I have told you, if we take this plane as the yz plane, then x axis is a perpendicular axis passing through the center of the loop. So this is nothing but the axis of the loop. Okay, so on the axis of the loop, this is the value of the magnetic field, and as you can see, it's always in the direction of the axis. Okay, now so far it's okay. Now if somebody asks what is the value of the magnetic field at the center of the loop, so if someone asks to find the value of the center of the loop, then this P point will be at O. So the difference between the point O and P will be 0. So x is 0 in that case. Okay, for center of the loop, x is equal to 0. So to find the magnetic field at the center of the loop, you have to just put the value x is equal to 0, then you can find out the value. Okay, let me do it again. The magnetic field at the center of the loop, B center, will be equal to mu naught into I divided by 2 a square plus x square is equal to 0 to the power 3 by 2 into I cap. Okay, so it's come very nice expression to a square to the power 3 by 2 means a cube into a square I cap. Okay, so mu naught I divided by twice a into I cap. This is the magnetic field at the center of the loop. This is a very important expression. Okay, you have to remember it. Very important. Magnetic field at the center of the loop. If you remember, the magnetic field due to a current carrying wire at a distance r, it was how much? Mu naught into I divided by twice pi into r. Okay, it was magnitude of the magnetic field. Okay, in this case the magnitude is mu naught into I divided by twice a, and its direction was along the axis of the loop. Okay, so this expression you have to remember. There will be many numerical problem based on this expression, and I am going to do those numerical problem after I discuss a little more topic. Okay, next class I am going to discuss about two different kind of devices. One is solenoid and another will be toroid. Okay, these two devices I am going to discuss in the next part of the video, and after that we are going to do the numerical examples. numerical examples on based on the topic which I have taught you till now. So another one class I am going to upload the videos on YouTube, and after that for doing the numerical example I am going to have you on a Google Meet. Okay, on Google Meet we are going to basically solve the problem, because one-to-one interaction is very important for solving the numerical example. Okay, so far this is okay, and the next part of the video I am going to discuss solenoid and toroid, and after that I am going to do numerical example on an one-to-one meet on Google Meet. Okay, so thank you so much.